Polynomial Theory, Part 2. The theorems that we'll be discussing in this demonstration are the upper and lower bounds theorem, Part 1, upper lower bounds theorem, Part 2, and Cauchy-Bounds theorem. The upper lower bounds theorem, Part 1 statement goes something like this. Suppose p of x is a polynomial of degree n greater than or equal to 1. If we perform synthetic division on p of x by x minus b, where b is positive, and if the results of synthetic division are all 0 or positive numbers, then b is an upper bound for all positive real solutions. If we perform synthetic division on p of x by x minus a, where a is a negative quantity, and if the results of synthetic division are alternating in sign, then a is a lower bound for all real solutions. Let's look at an example. Is 5 an upper bound for all real solutions to the polynomial p of x equal to x cubed minus 4x squared plus 2x minus 3? Let's perform synthetic division, and we have our synthetic division table here. And in the bottom row of this table, we see the results of synthetic division. Now, according to the theorem, if all of these numbers are 0 or positive, then we do satisfy the condition for 5 being an upper bound. And since the third row in the table are all positive, we may conclude that 5 is an upper bound for all real solutions to the polynomial. Continuing with this polynomial, we're going to ask, is negative 3 a lower bound for the real solutions to the polynomial x cubed minus 4x squared plus 2x minus 3? If we perform synthetic division, we see the synthetic division table here, and our bottom row there has alternating signs, starting with positive, then negative, then positive, then negative, and this satisfies the conditions of the theorem. Since the signs alternate in the third row of the table, we may conclude by the theorem that negative 3 is indeed a lower bound to all real solutions for this polynomial. Both of these examples combined dictate that all real solutions to x cubed minus 4x squared plus 2x minus 3 are in the interval negative 3 to 5. So the red interval highlighted on the x-axis represents the bounding interval for all real solutions to the polynomial. So all the solutions, all the real solutions anyway, to this polynomial have to be somewhere on this red line. The upper lower bounds theorem part 2 statement is given here, and this provides a bound for all complex solutions. So that includes your real ones as well as your imaginary ones. And it goes like this. Suppose p of x is a polynomial of degree n greater than or equal to 1. Then all complex solutions to p of x will lie in a disk centered at the origin in the complex plane, whose radius is determined by this formula. You take the maximum of the absolute value of all coefficients, divide out the absolute value of the leading coefficient, and then add 1 to that result. And that will be the radius of the disk that will encapsulate all solutions to the polynomial. Determine the radius of the disk containing all the solutions to the polynomial x cubed minus 1. Now, according to the formula, we take the maximum absolute value of all the coefficients of the polynomial. So in my example here, the coefficients are all either 1 or negative 1. And we take the absolute value of each one of those. In this case, we get 1. And then we take the maximum of that, which is 1. And then we're going to divide by the absolute value of the leading coefficient, in this case 1. So we have 1 divided by 1, and that's 1. And then we add 1 according to the formula, and that gives us 2. So the radius is 2, and all solutions in the complex plane are in a circle of radius 2. The red circle that you see in the graph here is this bounding circle or disk. The blue dots are the actual solutions to the polynomial in the complex plane. If you notice, my axes are labeled with the real axis being horizontal, the imaginary axis being vertical, and the blue dots again are the solutions, and the red dashed circle is the results of our bounding circle. All of the solutions have to be inside this disk according to the theorem. Let's look at another example. Determine the radius of the disk that has all the solutions to the polynomial x cubed minus 4x squared plus 2x minus 3. According to the formula, we have the absolute value of all the coefficients, 1, -4, 2, -3. So take the absolute value of each one of those, and then take the largest of those. In this case, it's 4. Divide by the absolute value of the leading coefficient, in this case 1, and you get 4 divided by 1, which is 4. And then add 1 to that, and you get 5. So the radius is 5. So all solutions to this polynomial are contained in a circle of radius 5, centered at the origin in the complex plane. And again, here we have our axes set up with the real and the imaginary components. We have our bounding circle, where in red here, and we also have our solutions, which are blue dots. So we have contained all the solutions inside this red circle. Let's look at another example. Determine the radius of the disk containing the solutions to the polynomial 3x to the 5th minus 4x to the 4th plus 2x cubed minus 7x squared plus 10x minus 6. According to the formula, we may do the following. Take the absolute value of each of the coefficients, in this case 3, -4, 2, -7, 10, -6. Take the largest of those in absolute value, in this case it is 10, and then you divide by the absolute value of the leading coefficient, in this case 3. And then you add 1 to that, so you have 1 plus 10 over 3, and that is 13/3. So the radius is 13/3, a little bit bigger than 4. The red circle again is the bounding circle in the complex plane, and the blue dots represent the actual solutions to the polynomial. So here we can see the red circle has enclosed all the possible solutions to this polynomial. The Cauchy bounds theorem is stated below. Suppose you have a polynomial whose leading coefficient is 1. Then a bound on the zeros of the polynomial is the smaller of these two quantities. So you may consider either the maximum value of 1 or the sum of the absolute values of all of the coefficients of the polynomial except the leading coefficient. That is one of your choices. Or you may consider the absolute value of all of the coefficients except the leading coefficient. Take the largest of those and then add 1 to it. So here are your two choices, and you choose the smaller of these two after you have done the arithmetic for these two choices. Let's see this in action. Determine the interval containing the solutions to the polynomial x to the 4th minus 2x cubed plus 4x squared minus 5 by using the Cauchy bounds theorem. We first evaluate the expressions given in the theorem, and we have one evaluated here for us. So we take the maximum of 1 or the sum of all of the coefficients except the leading coefficient. So we have -5 for the constant, 0 for the x, 4 for the x squared coefficient, and -2 for the x cubed coefficient. We add all those up after we take the absolute value, and we get 11. So we choose the maximum value between 1 and 11, and of course that's 11. Our other possibility is that we take the maximum of the absolute value of all of the coefficients except the leading coefficient. And we have the absolute value of -5, the absolute value of 0, the absolute value of 4, and the absolute value of -2. We go ahead and choose the maximum of those, which is 5 in this case, and then we add 1 to that and we get 6. Since 6 is smaller than 11, all the roots to the polynomial are in the interval -6 to 6. And that is how you use the Cauchy-Bounds theorem when it's stated in this fashion. Let's look at another example. Consider the polynomial 4x to the fifth minus 2x cubed plus 2x squared plus 1. Use the Cauchy-Bounds theorem to determine the interval where all roots of the polynomial are located. First, we need to make the leading coefficient of the polynomial 1. Remember, the theorem only applies to when the leading coefficient is 1, so we have to make it 1, and this is done by factoring out the 4 from each term in the polynomial. And here we see the polynomial, and then we see the 4 factored out. Now we may examine the polynomial in parentheses, and this is true because the 4 is merely a vertical stretching factor, and it does not affect the location of the roots itself. We first determine the values of the expression given in the theorem. So here we have the maximum of 1, or the sum of the absolute value of the coefficients. 1/4 plus 0 plus 1/2 plus absolute value negative 1/2 plus 0. Add those all up, and you get the maximum value of either 1 or 5/4. And of course that is 5/4. Now we examine the other possibility given in the theorem. If we take the maximum of all of the coefficients after considering the absolute value and then add 1 to it, as shown here, we get 3/2. And now we pick the smallest of the two results. Which one's smaller, 5/4 or 3/2? In this case, the result is 5/4. So all roots to this polynomial are in the interval -5/4 to +5/4. Thank you for your time and attention.